All right, so imagine this, right? A place on the periodic table where elements can stick around for years, maybe even eons.
Eons, wow.
Yeah, we're talking about the island of stability.
Right.
And it's had physicists kind of going crazy for decades.
For a long time. It's a fascinating concept.
It really is, and you sent over some really interesting research on it.
Absolutely. Happy to share it.
So let's do a deep dive into how this theoretical island could totally change how we think about, like, matter itself.
Yeah, I mean, the island of stability is basically this region where some super heavy elements, those that are, beyond uranium, they're predicted to have way, way longer half-lives than their neighbors on the periodic table. You see, most super heavy elements decay almost immediately, in fractions of a second.
Right. Super unstable.
Yeah, exactly. But this island suggests that some might hang around for a lot longer, all thanks to this idea of magic numbers.
Okay, magic numbers. Now, I vaguely remember from chemistry class that stability has something to do with how protons and neutrons are arranged in the nucleus.
You got it. You're on the right track.
Yay.
The stability of a nucleus really all comes down to its binding energy.
Binding energy.
It's essentially a measure of how tightly those protons and neutrons are held together in the nucleus.
Okay.
So higher binding energy, more stable nucleus. Pretty straightforward, right?
Makes sense.
And, think of it like a Jenga tower.
Okay, I like that.
Too many blocks, too few blocks. You put it on the wrong spot, and the whole thing, gets wobbly.
Yeah, it's going to fall apart.
Exactly.
So are you saying that as we go up the periodic table to those heavier elements, things get a bit, unstable?
Yeah, exactly.
Yeah.
Because you're cramming more and more protons and neutrons into the nucleus, and so things get a little shaky.
Yeah. I mean, I know that elements beyond lead, which is element 82,
Right.
they tend to be super unstable.
That's right. The binding energy generally goes down as we go to heavier elements. And that leads to them, falling apart more easily. But the island of stability theory, it throws a bit of a curveball. It suggests there are, exceptions to this trend. The idea is that specific numbers of protons and neutrons, magic numbers,
Right.
they create these super stable configurations within the nucleus.
So these magic numbers, they act like what? Like a stabilizing force?
Yeah, exactly. Like a secret ingredient for super heavy element.
Okay, so I'm seeing in my notes here something about electron shells.
Right.
How does that tie in?
Good point. So it's kind of similar to the way electrons fill those shells in an atom, right?
Yeah.
When a shell is full, the atom is more stable. Same idea here. Just swap electrons for protons and neutrons.
Got it. So full shells, happy nucleus, stable element. Pretty neat.
That's the gist of it.
I'm also seeing that physicists Maria Gilbert-Mayer and Johannes Hans Daniel Jensen,
Oh, yeah, pioneers.
they won a Nobel Prize for their work on the nuclear shell model back in the 60s.
That's right, 1963.
And their research, that really laid the groundwork for this whole island of stability idea, didn't it?
Oh, absolutely. It's foundational. Their work, along with later stuff by, William Myers and Uadisa Shuiteki, it all kind of led to this prediction.
And what was that prediction?
That element 114,
Element 114.
flerovium,
Flerovium. Okay.
with a neutron number of 184.
184 neutrons.
That could be a particularly stable spot right on that island.
So flerovium, this is kind of like a landmark element in the whole search for the island of stability.
Yeah, exactly. I mean, there's a good reason for that.
Okay.
Back in 1998, scientists at the Joint Institute for Nuclear Research
Okay.
over in Russia,
Yeah.
they actually managed to create flerovium,
Wow.
synthesized it, and its properties. Well, they kind of shook up the physics world.
Okay, I'm intrigued. What was so special about flerovium?
Well, think about it. Super heavy elements, they usually decay super fast, right?
Right, fractions of a second.
But flerovium, it stuck around for, get this, 30.4 seconds.
30 seconds. That's like a lifetime for a super heavy element.
I know, right? It's an eternity. And that's why it was such a big deal. It really pointed to these stabilizing magic number effects that had been predicted. All that work by Mayer and Jensen and others, it was all coming together.
That's incredible. So flerovium wasn't just another element on the periodic table.
Nope.
It was a crucial piece of evidence for the island of stability.
Exactly. A real game changer. And the excitement, it just kept building. Scientists have found even heavier elements since then, getting closer and closer to that magic neutron number of 184.
184, yeah.
For example, there's this isotope, 285 CN. Just 8 more neutrons than its counterpart, 277 CN.
8 more.
And boom, its half-life is almost 100,000 times longer. Talk about a difference.
That is wild. just a handful of extra
It
neutrons.
really shows you the power of those extra neutrons, especially when you get close to those magic numbers.
It's like they're the glue holding these super heavy elements together.
Yeah, you could say that.
But hold on, we've been talking about atomic nuclei as if they're these neat little spheres. Is that always the case?
Ah, you've hit on a really important point. Not all nuclei are perfect spheres.
What? Really?
Yeah. In fact, some of them, especially in the superheavy realm, they can be deformed. Like, imagine football shapes or pears or,
Yeah.
all sorts of wonky shapes.
Okay, so we've got wonky nuclei.
We do. And it throws another wrench into our understanding of the island of stability.
So how do these deformed nuclei change things?
Well, they actually lead to different magic numbers.
Different magic numbers.
Yep. Totally new possibilities for stability in the superheavy elements.
Wow, so it's not just one island of stability.
Right.
It's more like an archipelago of stability
Right.
with spherical islands and deformed islands.
You got it. And the discovery of hassium-270, that really solidified this idea. It's believed to be doubly magic. That means it has magic numbers of both protons and d neutrons,
Okay.
but it's deformed.
So hassium-270 is like the rebel of the super heavy world, breaking all the rules.
Yeah, you could say that.
Yeah.
And its half-life is surprisingly long, 9 seconds, which just adds more weight to the idea that these deformed nuclei can hold the key to new islands of stability.
This is blowing my mind. It's like the more we learn, the more we realize we don't know. But if we do find elements with these super long half-lives on these islands, how would they actually decay? It can't be a peaceful process, right?
You're right, it's definitely not peaceful. Super heavy elements, they've got a few tricks up their sleeve when it comes to decay. You've got your classic alpha decay,
Alpha decay.
where the nucleus ejects an alpha particle, basically a helium nucleus.
Right.
Then there's spontaneous fission, where the nucleus just splits apart.
Yikes. Sounds kind of violent.
Yeah, it's pretty intense.
But I bet it gets even crazier with the really, really heavy element.
Oh, absolutely. For the heaviest of the heavy, you can even have cluster decay.
Cluster decay, okay.
That's where the nucleus ejects a whole chunk of itself, like a cluster of protons and neutrons, not just a simple alpha particle.
Wow. Atomic fireworks.
Exactly. So even if these island elements are long-lived, they don't go quietly.
Definitely not. But here's a question that's been bugging me. If these island elements DO exist and they have these super long half-lives, could we actually find them in nature?
That's a great question, and it gets a bit complicated. You see how elements are created in stars through a process called the R process.
Okay.
It doesn't really favor creating these super heavy nuclei.
It's not impossible, but
It's like trying to build a skyscraper with toothpicks.
not the best building material.
Yeah. The conditions just aren't right. So while these island elements might exist naturally, they'd be incredibly rare. Finding them would be like finding a needle in a haystack. A very, very large haystack.
Okay, so probably not something I'm going to stumble upon on my next nature hike.
Probably not. But the fact that we can create these elements in labs, even if it's for a short time, it's pretty amazing. It really speaks to human ingenuity.
It really is mind-blowing. So if we want to keep exploring this island of stability
Yeah.
and maybe find those elements with lifetimes longer than billions of years,
Billions of years.
we're going to need some brilliant minds and some pretty incredible technology.
Absolutely. And that takes us to the next chapter of our deep dive. The challenges, the ingenious solutions, and the whole process of creating these super heavy elements. I think you sent me some research on stuff like radioactive ion beams and multi-nucleon transfer reactions.
Yeah,
Right.
definitely sounds pretty cutting edge.
It is. It's fascinating stuff.
So radioactive ion beams, multi-nucleon transfer reactions, those sound pretty intense.
They are. They are. And it's, it's not like we can just smash a couple of atoms together and boom, new element.
Right, right.
There's a lot more to it.
Way more to it.
And one of the biggest challenges is getting enough neutrons into the nucleus.
Ah, right, those magic numbers.
Exactly.
Yeah.
And they depend on both protons and neutrons being, well, just right. Like a recipe.
The perfect recipe for atomic stability.
Exactly. That's a good way to put it. And, our current methods, they've gotten this to oganesson, element 118,
Mm-hmm.
but we kind of hit a wall when it comes to packing in more neutrons.
So it's like we're trying to cram too much into a tiny space.
Yeah, it's a bit like, imagine trying to build a house of cards,
Okay, I like this analogy.
but in a windstorm.
Yeah, not going to end well.
Not very stable.
No, no. So how are scientists tackling this neutron shortage?
Well, that's where things get really interesting.
Okay, good.
You mentioned radioactive ion beams,
Yeah, they seem to be getting a lot of attention.
and for good reason. They're a game changer.
Okay.
So instead of using those stable beams, the ones we use now in accelerators, scientists are looking at radioactive beams.
Radioactive beams. Okay.
Think of it this way. Right now, we're building with, let's say, standard bricks.
Standard bricks. Okay.
But what if we could use bricks that already had, like, mortar pre-applied?
Oh, I see. So it's like giving those nuclei a head start.
Exactly. That's what radioactive ion beams do. They're more neutron-rich from the get-go.
Yeah.
So there's a better chance of getting those heavier, more neutron-packed nuclei that we need.
Okay.
And then there's multi-nucleon transfer reactions.
Multi-nucleon. All right. Break that down for me. That one sounds pretty complex.
It is. It is.
Yeah.
It's imagine instead of just fusing two nuclei together,
Okay, yeah.
you have this, like, more intricate exchange going on.
Yeah.
Multiple protons and neutrons are being swapped between those colliding nuclei.
Okay. So it's more of a, what, like a chaotic dance?
Yeah. More of a dance, less of a head-on collision.
Mm-hmm.
It's a messy process for sure.
Less like building blocks, more like a game of atomic billiards.
You got it. You're good with these analogies.
I try. So all this talk of smashing atoms, it makes me wonder,
Yeah.
could we, like, recreate what happens in stars to make these island elements?
That is an interesting thought. And some scientists have actually proposed that, using, well, controlled nuclear explosions.
Whoa, whoa, whoa. Hold on. Controlled nuclear explosions.
Yeah. To mimic the R process, the rapid neutron capture process. You know what happens in supernovae?
So basically, recreate a supernova in the lab. That's ambitious.
Super ambitious.
Yeah.
It's definitely not easy.
Yeah.
The technology is very complex.
I can imagine.
And then you have all the, ethical considerations and all that. But it's not impossible.
So the island of stability,
Yeah.
it's not just pushing the boundaries of science. It's like pushing the boundaries of technology and ethics as well.
Yeah, that's a big one.
Right.
A lot to think about. But, the potential rewards are huge.
Absolutely. So we've talked about the what,
Right.
and we've talked about the how.
How? Yeah.
But what about the why? Why are scientists so obsessed with this island of stability?
I think it boils down to, like, pushing the limits of what we know. Imagine finding these super heavy elements, and they live for longer than the Earth has existed.
Wow.
It's like it would rewrite the textbooks, right? It'd be like discovering a hidden dimension.
Yeah.
Something completely new about reality that we never even knew was there.
It's almost philosophical.
It is. It
Mhm.
really is. But then, beyond the fundamental science, there's also the potential application.
Okay, now you've got my attention. Applications. What kind of applications?
Well, this is all speculative, of course. But some scientists think these super heavy elements could be used for things like energy production, or new tools for medical imaging and treatment, maybe even catalysts for brand new chemical reactions. Who knows?
So it's not just knowledge.
Right.
It's also about potential innovation.
Exactly. And that's what makes it so exciting to work on. It's driven by human curiosity, ingenuity, and this desire to discover the unknown.
And speaking of the unknown,
Right.
we've done a pretty deep dive into the island of stability.
We have. It's a lot to take in.
It is. But before we finish up, is there anything else that our listeners should know about this? Anything they should keep in mind?
I think it's important to remember that this is a field that's constantly changing. What we know today about the island of stability, it's just the beginning. New discoveries are happening all the time, and our understanding is, always evolving.
It's like we're watching a scientific thriller. But in real time, every experiment could be a plot twist.
That's a great way to put it. It's exciting to be a part of. We're literally seeing the frontiers of human knowledge being pushed back.
Amazing.
Yeah. And who knows what incredible discoveries are waiting for us in the future.
Yeah, it really makes you appreciate the power of human curiosity.
It does. It does. Always pushing forward, even when it seems impossible. And I think the island of stability is a perfect example of that.
Definitely. I mean, this drive to explore and understand, even when the answers seem so far away.
Absolutely.
Yeah.
It's a good reminder that we still have so much to learn about the universe.
Yeah, so much. And that sometimes the journey is just as important as the destination.
Couldn't agree more.
So I think our listener has a pretty good grasp of the island of stability now.
I hope so. It's a fascinating topic.
But before we wrap up, I'm always curious, what was the most interesting part for you? What really stood out?
Oh, that's a good question. I think for me, what's most amazing is just the sheer audacity of it all.
Audacity, okay.
Yeah. I mean, we're talking about creating elements that don't even exist naturally here on Earth. Elements that push the boundaries of what we thought was possible in terms of, how stable matter can be. It's just incredible what humans can do. And that drive to be curious, to find out more, that's what makes it all happen.
It really is incredible. I mean, creating these elements that we thought were impossible.
Yeah, impossible
Even
elements.
if it's just for a tiny fraction of time.
It's still amazing.
It makes you wonder, what else will we discover in the future? What other impossibilities will we figure out?
That's the exciting part. Who knows what's out there?
And that brings us to our final thought for today.
Okay.
What if, and just imagine this for a second,
All right, I'm imagining.
what if we actually reach the island of stability and these long-lived, super heavy elements, they become more than just a scientific curiosity?
Okay, yeah, I'm following you.
What could they mean for our world?
Oh, wow. That's a big question.
Right. I mean, could they revolutionize energy, lead to medical breakthroughs, unlock technologies we haven't even thought of yet?
It's a lot to consider, but it's exciting, right? I mean, the possibilities are almost limitless.
It is exciting and, to be honest, a little bit daunting too.
Yeah, I get that. It's a lot to take in.
The island of stability, it's not just about physics. It
Yeah.
could change everything.
It really could. The way we understand the universe, the future of technology, all of it.
Well, on that note, a huge thanks to our listener for joining us on this deep dive into the island of stability.
Yes, thank you for listening.
It's been an amazing journey, and I hope you've enjoyed exploring this incredible world with us.
Yeah, me too. Until next time.